All right, ladies and gentlemen, welcome to the last lecture in our discussion of atomic theory here. This is our discussion of quantum numbers. The purpose of this lecture is to be able to describe the characteristics of electrons within an atom in terms of a unique set of four quantum numbers that are derived from the solutions to the Schrodinger wave function equation. So the key idea here in our discussion today is that when we solve that Schrodinger wave function equation, we get solutions to that equation which include several variables, and each of those different variables tells us something different about the electron within that atom. You can kind of think of these quantum numbers as being kind of a unique address that is a set of pieces of data that tell us things about like where the electron is found on average from the nucleus, the shape of the orbital, that is the probability of finding the electron in any given region in space around the nucleus, the orientation in space of that orbital, and the direction the electron is essentially traveling. So the big idea here is we want to be able to give essentially each one of these electrons kind of its own unique address. And we're going to kind of go through and look at these different quantum numbers, and you'll notice that several of these quantum numbers are things that we've actually come into contact with earlier in our discussions of quantum theory. The first quantum number we get, the first variable from that Schrodinger wave function equation, is what we refer to as the principal quantum number that has the symbol n in the system. And that principal quantum number is an indication of, on average, how far from the nucleus that electron actually exists. We've seen this kind of from our Bohr model atom discussions as being kind of an equivalent of the shell of electrons from a Bohr model atom, where the lowest energy shell would be referred to as n equals 1, the shell closest to the nucleus. And then as we move to subsequent shells further to the outside, we end up with values that increase in number from n equals 1 to n equals 2 to n equals 3. And you'll notice that there are only specific allowed values for these quantum numbers. That is, they're quantized. You can have an electron in the first shell or in the second shell, but you can't have an electron with the principal quantum number n equals 1.5. That is not a valid solution to the Schrodinger wave function equation. So the allowed values for this principal quantum number go from 1 up to essentially infinity. And again, we're starting with the electron closest to the nucleus, where we have principal quantum number 1. So, principal quantum number, something we've seen before. The second quantum number you solve for when you solve the Schrodinger wave function equation is what's called the azimuthal or shape quantum number, L. The solutions to this portion of the equation yield a series of different, again, distinct values, quantized values, which start with the lowest possible value of the shape quantum number of 0, which refers to an s orbital, and increase up to an allowed quantum number of n minus 1, in which n is the value of the principal quantum number. So that is to say, if you're in the first period, where n equals 1, the first shell of electrons in your atom, the allowed values for the azimuthal shape quantum number will go between 0 and n minus 1. So again, if n is 1, that would be between 0 and 0, which means the only allowed value for the shape quantum number in the first principal quantum number would be a value of 0. That is to say, the only orbital that exists in the first period, the first energy level, is an s orbital, a spherically shaped orbital. But if you move up to the second principal quantum number, that is the second shell of electrons, then the allowed values for the azimuthal quantum number will go between 0 and n minus 1, which will now be 2 minus 1, or 1. So in the second shell of electrons, we see the existence of not only s orbitals, but also of p orbitals. And you can kind of see this process continuing along, which correlates directly to your electron configuration details we've discussed. In the third shell, we see the existence of both sp and also d orbitals, so the allowed values go between 0 and 2 in the third shell of electrons. And when n is equal to 4, we would see allowed values of the shape quantum number go between 0 and 3, which means we have, in the fourth energy level, sp, d, and f orbitals, corresponding to values of those quantum numbers of 0, 1, 2, and 3. So taken together, these two quantum numbers, n and l, tell us the shell of the electron and the shape of the orbital that electron occupies. The third of our quantum numbers is given the abbreviation m sub l, which stands for the magnetic quantum number. That magnetic quantum number describes the orientation in space of that particular orbital. And if you remember back to our discussions of the orbitals from our modern atomic theory discussion, recall back to that p orbital. The p orbital, we said, could be oriented along the x, the y, or the z axis, and we discussed those as a p sub x, p sub y, and p sub z orbitals. And those three suborbitals there all occupy different orientations in space, and those correspond to different values of that magnetic quantum number. So the allowed values for the magnetic quantum number of that orbital go between values of minus L and positive L, where L is the value of the shape quantum number. So again, looking at those p quantum numbers, those p orbitals have a value of 1 for the shape quantum number, which implies the values of the magnetic quantum number for a p orbital will go between minus L, or minus 1, up to positive 1. And therefore, there are allowed values of negative 1, 0, and positive 1, which correspond to the x, the y, and the z orbitals. And likewise, if you have d orbitals, recall that there are 5 suborbitals within a d shell. For those d orbital electrons, the allowed values for the magnetic quantum number will go between minus L, where L is 2, in this case, for d orbital, through positive L, which would be positive 2. And therefore, for that d orbital, the allowed values for the magnetic quantum number will be negative 2, negative 1, 0, 1, and 2, for a total of 5 orientations in space, that is, 5 suborbitals present within our d orbital. So we've got principal quantum number, distance from the nucleus, shape quantum number, shape of the orbital, magnetic quantum number, orientation in space of the orbital, and the last quantum number we have to deal with here is what we refer to as the spin quantum number. That spin quantum number is related to the angular momentum of that electron. We define it as either being spin up or spin down. Note here, guys, that up and down is really arbitrary, since this electron doesn't really know what's up and what's down. But really the key idea here is, if you remember from our discussion of electron diagrams, the total number of electrons that can fill any given orbital are 2, and we said those orbitals are identified by their spin in opposite directions. Truly here, guys, we're not really treating these electrons as particles that are truly spinning in a circle, like we would from a kind of solar system model of the atom. But the key idea is that those electrons are in fact charged particles, and moving charges generate magnetic fields. So the key idea from the spin quantum number is that the magnetic field generated by that charged electron as it moves is either going to be in one of 2 mutually opposite directions. And we define those as what we call, again, spin up and spin down. And the values of that spin quantum number derived from our Schrodinger equation come out as values of either minus 1/2 or positive 1/2. The minus 1/2 are spin up, and the positive 1/2 are spin down. So those are the 4 quantum numbers we get when we solve these solutions to the Schrodinger wave function equation. And the key idea about those quantum numbers is that for any given atom, no 2 electrons within that same atom can share the exact same set of 4 quantum numbers. That is, each electron has its own unique address defined in terms of those quantum numbers for any one for any one electron within the atom. We call this the Pauli exclusion principle. And it's called an exclusion principle because essentially once an electron has a given set of 4 quantum numbers, it excludes all other electrons from sharing that same set of 4. So let's go ahead now and take a look at how we can define what those 4 quantum numbers are for a given electron within a electron configuration for an atom. Note here, guys, now every single electron in the atom has a set of 4 quantum numbers. We're just going to focus on the very last electron, that is the highest energy electron, and defining those quantum numbers for these particular atoms. So let's start with magnesium. Have a look for me, please, on your periodic tables and find the element magnesium. Magnesium is element number 12. And let's go ahead and give magnesium's electron configuration here. Following the Aufbau process from the ground up, our electron configuration would be 1s2, 2s2, 2p6, followed by 3s2. And again, every single one of those electrons in there has its own unique set of 4 quantum numbers, But let's just focus on the last filled electron there, that is the highest energy electron. That is our 3s2 electron. We're going to go ahead now and define the four quantum numbers n, l, m sub l, and s. So to begin, our principal quantum number n, that tells us the shell of electrons that we're looking at here. The principal quantum number n is given as the coefficient before the shape of the orbital within our electron configuration, which implies for this electron, the highest energy electron in magnesium, the highest energy shell is the third shell. So we have a principal quantum number of 3 for this electron. L, the shape quantum number for this s orbital, the shape quantum number for that s orbital is given as a value of 0 off of our chart up here. So for a shape quantum number of 0, that would imply to us we now have an s orbital for that highest energy electron. And the trick to doing these is that the last two quantum numbers need to be determined simultaneously. The highest energy electron in our configuration was the second electron in that 3s orbital. And if you recall from back when we looked at our Aufbau diagrams, those electrons filled first spin up, then spin down. So if you go ahead and take a look for me, please, on your handouts that you received in class that had the Aufbau process. Also on that handout, we have a table of how to determine quantum numbers for these different elements. And so what I want you to do here is to take a look at that table and see where we're at so far. We determined that we are in the third shell in an s orbital, which gave us a 3 and a 0 for n and l. And as I mentioned here, guys, we're going to determine m sub l, that is the orientation in space, and s, the spin, simultaneously. We are the second electron in that s orbital, which implies we're going to start counting from the top down here. Counting from the top down will give me electron number 1, electron number 2. So the value of m sub l, that is the orientation in space, is always going to be for an s orbital 0. And the reason why that's the case is because there's really only one direction you can orient a sphere in space. If you rotate it, it looks exactly the same as it would in any other rotation. So the value of our orientation in space, that is the magnetic quantum number, comes out as a value of 0 for every s orbital. And then the spin, again looking back to our table here, the spin is neatly divided through this central line on your table right here. The first electrons above this line are all given as spin up. The electrons below that line are filling spin down, which implies that second electron in the s orbital is going to be filling spin down for a value of spin of positive 1/2. So we've got our four quantum numbers for this 3s2 electron within the magnesium atom are 3 for the principal quantum number, 0 indicating an s orbital, 0 for the orientation in space, and s, which is a spin of positive 1/2 for spin down. Now that set of four numbers, guys, is not just arbitrary nonsense. It really means something about the electron. This tells me that this electron is in the third shell of electrons in an orbital shaped like a sphere, oriented, the only way we can orient a sphere in space, so that really doesn't come to play in this one, with a spin, which is generating a magnetic field, which we would call spin down. Okay. So, first example done. Let's go ahead and take a look at a second example. Well, let's look at element HO, which is holmium. Holmium on your periodic tables is element number 67, which means we've got a big electron configuration to deal with here. So let's go ahead and use our noble gas shortcut, going back to the previous noble gas back before holmium. Before 67, you go all the way back to element number 54, xenon, on your electron configurations here for your periodic table. So we're going to follow element number 54, which is xenon, and then following along in your periodic table or your Aufbau sheet, after 54 comes 55, which is cesium. That would give us a now 6s2 electron. Following these 6s orbitals, we move down now into the 4f orbitals, and if you count over for holmium, we are in the 11th position within that 4f orbital. So we have 4f11. And again, double check your electron configuration against the one given on your periodic table. You'll see that holmium is in fact not an exception to the electron configuration rules. So let's go ahead now and look at that 4f11 electron. That is the highest energy electron within this electron configuration. And let's define its set of 4 quantum numbers, N, L, M, and S. So, for the 4f11 electron, the principal quantum number, the shell of electrons we're looking at here, again, is given by our coefficient. That is the 4th shell of electrons. The shape quantum number L describes the shape of our orbital. For an f orbital, looking on your sheets again, f orbitals are given a shape quantum number of 3. So when we solve the Schrodinger wave function equation, this comes out as an f-shaped orbital. Remember, these are either the 8-leaf clovers or the dumbbell with the double donuts. So we've got a 3 there. And then again, we're going to determine the orientation in space and the spin simultaneously. We are the 11th electron in this 4f orbital. So again, looking at your diagrams here, we're going to count down now, starting from the top of the f orbital here, going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we are now 11 electrons in, which yields an orientation in space of a value of 0, and a spin below that line of division, which is a spin of positive 1/2. So our last 2 values here for the quantum numbers are a 0 for the orientation in space and a spin of positive 1/2. And if you'll take a look here for a quick moment at another slide from a previous lecture, you may remember from our previous lecture on modern atomic theory that we looked at the different shapes of these orbitals, and we gave you this kind of artistic rendition of what these orbital shapes look like, these probability cloud distributions. Have a look here, guys, and we'll kind of see how this diagram here correlates to our quantum number chart. Recall that the allowed values for the orientation in space, that is m sub L, the magnetic quantum number, went between negative L and positive L, right? So if you look at an s orbital where L equals 0, the only allowed value for the orientation in space quantum number would be a value of 0, showing us that there's only one orientation in space for that s orbital. But for a p orbital, where the shape quantum number is 1, there are in fact 3 orientations in space, because the allowed values for that magnetic quantum number go between -1 and +1, which would imply, therefore, values of -1, 0, and +1 correlating to the p sub x, p sub y, and p sub z orbitals. And again, looking at that f orbital, which we were just dealing with for holmium, that 4f11 electron, for f orbitals, the value of the shape quantum number was a 3, which implies the allowed values would be between -L and positive L for the orientation in space, which correlate to -3, -2, -1, 0, +1, +2, and +3. So in describing that holmium electron, essentially what we said is that it's the 11th electron in here, in the f orbital, so we would be looking at electron 1, 2, 3, 4, 5, 6, 7, all spin up, followed by 8, 9, 10, and 11. So essentially the electron that we are describing here is that 11th electron in this f orbital, which is shaped like that dumbbell with the double donut, which happens to be the electron which is spin down within that particular orbital. So again, that description we make of the 4 quantum numbers is not an arbitrary set of 4 numbers. It really describes something real about those electrons. That is, this electron was in the 4th shell of electrons in an F orbital, a dumbbell with a double donut, which was oriented along that axis, spinning, generating a magnetic field which we would refer to as spin down. All right, so at this point we now know how to assign quantum numbers based upon the electron configuration for an atom. The last thing I want to look at here is a result of those quantum numbers here. We're going to go ahead and now describe the magnetic moment of the electron. As it turns out, guys, some atoms inherently exhibit a magnetic dipole, whereas others don't. We define species that are attracted by an external magnetic field to be paramagnetic, whereas species that are repelled from that external magnetic field, we call those things diamagnetic. And the reason why atoms end up as either being defined as paramagnetic or diamagnetic has to do with the pairing of electrons in terms of their opposite spins. If you think about it, an electron is a charged particle, and as you might remember from your physics days, from your laws of magnetism, moving charges generate magnetic fields. If you have two electrons which are spinning in opposite directions, their magnetic fields point in opposite directions and thereby cancel each other out. So there's no net magnetic dipole for electrons that are paired off within an orbital. But that being said, if we have any unpaired electrons within that electron configuration, those unpaired electrons would be spinning in the same direction and thereby would create a net magnetic dipole for that atom. So what we're going to look at here is let's make a prediction about whether these two species here would be expected to be paramagnetic or diamagnetic based upon their electron configurations. So let's take a look first here at the element neodymium. Neodymium is an element from our lanthanide series that is an intertransition metal. Its element number is 60. And if we go back and look at our noble gas configuration for neodymium, the previous noble gas is xenon. And then following xenon on our periodic table to give the electron configuration after 54, we would end up at 6s2. And then moving down into the lanthanides, we would find that if after 6s2, we are in a position of 4f4 for that electron configuration of our neodymium atom. And at this point, it would be useful for us to imagine for a moment here, looking back to that Aufbau diagram we first used to describe the relative potential energy of these electrons. I'm going to go ahead and just kind of shorten this diagram here, giving you xenon's electron configuration. And then if you remember, that diagram went up in energy. Following xenon, we have that 6s orbital. And then after the 6s orbital, we have the 4f orbital, which again had 7 suborbitals within the shell. So this is our 4f shell. And all of the configuration up through xenon is filled, followed by, looking here at our valence shell, we're now at 6s2. Spin up, followed by spin down. And then within that 4f orbital, recall, the key idea here is all about Hund's rule that we follow, the bus rule that says the electrons will occupy an empty suborbital before pairing off with another, as long as it were the same given energy level. So within that 4f orbital, we're going to fill spin up, 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 and up for that 4f orbital. Now, all 4 of those electrons within that 4f orbital have the same spin, and those spins are unpaired with an electron spinning in the opposite direction, which implies this species has 4 unpaired electrons, which generate a net magnetic field. We would say, therefore, this species, neodymium, is paramagnetic. And we would therefore expect neodymium atoms to be attracted into an external magnetic field. Now let's contrast that now with a second species right here. That species is cadmium. Find cadmium for me, please, on your periodic tables. Cadmium is element number, let me find it here for just a moment here, 48 on your periodic table. And it is the end of the transition metals for period 5. So looking at cadmium's electron configuration, going back to the previous noble gas for cadmium, would be krypton. And then following krypton, element number 36, we move to rubidium and strontium, 37, 38, which are now in the 5s2, followed by into the transition metal family now, where the 10th element into the transition metal family, and we're n-1, which is 4d10. So cadmium is krypton, 5s2, 4d10 in terms of its electron configuration. And so again, looking at an energy diagram, we would have krypton's electron configuration representing all those lower energy electrons, followed by a 5s orbital, and then the 4d orbital. All those d orbitals have 5 subshells there. So within our 4d orbital, we would have that present as well in this cadmium atom. And so we're going to fill up these electrons following our Aufbau rule and Hund's rule. Spin up, spin down for the 5s2 electrons, and then for the 10d orbital electrons, they fill spin up, 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 up for the first 5, followed by down, 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 and down. And we recognize now that this entirety of the electron configuration for cadmium only contains electrons that are paired off within their suborbitals. That is, every single spin-up electron is paired with a spin-down electron. And because those two electrons generate magnetic fields in opposite directions, all those net magnetic fields will cancel each other out, and we would say, therefore, this species, cadmium, is therefore diamagnetic. And what we mean by diamagnetic would be that a cadmium atom itself would be repelled from an external magnetic field. So again, the key idea here is that the more unpaired electrons you have within a given atom, the stronger the net magnetic dipole would be for that particular atom, and therefore the more paramagnetic that species would be. And I believe that concludes now our discussion of magnetic moments and dipoles and quantum numbers. Thank you very much for listening.